Um, Good morning, everyone. I am Sharda from Tribal Welfare Degree College, Chennai. Guest lecturer in from Mathematics Department. I completed my MSc and pursuing my PhD. My online lecture topic is rings and fields. This is algebraic topic. Okay. So my topic is rings and fields. Now I want to share a few words and a few importance of rings and fields. What are the topics covered in these topics and how many characteristics, how many properties are there in this topic? We'll see. So first of all, I want to introduce what is rings and how many binary operators we have to use to build this topic. So actually already we discussed this total topic in groups. We have studied groups, which is in algebraic structure, on one binary operation. In groups, we will use only one binary operations, but in rings, we are going to use two binary operations. In groups, we used either addition or multiplication. And only by one binary operation we use either multiplication or addition, but in rings, both we are using at a time. And we have 8 properties completely. We'll see what are the properties, and we are going to see the definition of the rings. So this is the definition of a ring: a non-empty set or equipped with the two binary operations called addition and multiplication. It is denoted as addition, denoted as a plus, and multiplication denoted as equal dot, either star, anyone we can guess, is said to be a form of ring if the following properties are satisfied. The following, if we satisfy the following properties, we are going to finish. We are going to complete a complete ring. So first property is or is closed. We have to show this is closure property with respect to addition. Closure property with respect to addition. To satisfy the closure property, we need two elements, that is A comma B belongs to R. R is nothing but a ring. Then A plus B is belongs to R. What are the elements we are taking that is belongs to R? Next, addition is associative. We are going to satisfy here associative law. To satisfy the associative law, we need 3 binary operators, that is A comma B comma C. And associative law is form. The equation is A plus B plus C is equals to A plus B plus C. Left side we are going to put a open bracket to A plus B, and plus C is equals to A plus B plus C for all A comma B comma C belongs to R. Next, we are going to satisfy commutative law. Otherwise, we can say identity law and identity law. So here, to satisfy the commutative law, we need 2 binary operations, that is A comma B. The commutative law is A plus B is equals to B plus A. For all A comma B, both elements, whatever we are taking, that R belongs to R. Next, identity law with respect to addition. So these are properties we are taking only one binary operation. Till here we are using the one binary operation, that is plus. So identity elements, additive identity. Here in addition we are going to use identity element is 0. We can use E also. That is there exists an identity now denoted by 0 in such that 0 plus A is equals to A plus 0 is equals to B. For all A belongs to R. We are using one binary of one element A, and also we are taking 0. 0 is nothing but an identity. Okay, next. So next, fifth property we are going to use inverse property, that is additive inverse. Inverse with respect to addition. So here each element A in R, there exists an element minus A. So minus A is opposite of A. Inverse is nothing but what? It's the opposite. So minus A plus A is equals to plus A minus A is equals to 0. We have to find identity element, that is 0. Okay. So here A is minus A is inverse of A. So here till here we are going to satisfy 5 properties. That is what? Closure property, associative property, identity property, inverse property, commutative property. By these in these properties, we are using only addition. That is only one binary operation, that is nothing but addition. So next we are going to find closure property with respect to multiplication. Now onwards we are using multiplication symbol, that is nothing but dot. So here OR is closed with respect to multiplication, that is if A comma B is belongs to R, then A comma B belongs to A into B belongs to R. Next, associative with respect to multiplication. A into B into C is equals to A into B into C. Into is nothing but dot. A dot B dot C is equals to A dot B dot C. For all A comma B comma C belongs to, or all the three elements is belongs to R. R is nothing but what here? It is a ring. Next here we are going to use distributive law. That is for all A comma B comma C in R, A into B plus C is equals to A into B plus A into C. See here, what is the distributive law? A into B plus C is equals to A into B plus A into C. This is left distribution. And also we are going to solve the right distribution law. A plus C into A is equals to B into A plus C into A. That is nothing but right distribution law. So here we have one remark. If any algebraic structure R comma plus comma dot is called a ring, if R comma plus is an abelian group. By the first five properties, we are going to find abelian group, and all the properties below properties, I mean that is 6th, 7th, 8th properties is satisfied. Okay, so here all the 8 properties we have to satisfy to find the rings. So here we have types of rings. We have some types of rings. What are the types? Commutative ring. We have a commutative ring. Already we've seen in the properties, that is commutative ring. A ring in which A into B is equals to B into A for all A comma B belongs to R is called a commutative ring. Here into we are using. Next, and the two elements, that is also belongs to ring. Next, second one is ring with unity. So unity is nothing but what? 1. Okay, unity is nothing but 1. So if in a ring there exists an element denoted by 1, such that 1 into A is equals to A into 1 is equals to A. For all A belongs to R. Then R is called ring with unity element. Then the element 1 is belongs to R is called the unity element of the ring. So next, third property, null ring or zero ring. Null ring or zero ring. Null is nothing but 0 only. Null is empty. Empty set, that is. So the set R consists of a single element 0 with two binary operations denoted by a 0 plus 0 is equals to 0 and 0 into 0 is equals to 0 is a ring and is called null ring or zero ring. See here, by using these two properties, we are adding zeros and we are multiplying zeros. So after adding zeros, finally we are finding 0 only. After multiplying two zeros, we are finding 0 only. That is nothing but zero ring or null ring. So these are the properties, these are the types of the rings. Next, example of a rings. So here we are going to find some example of a ring. All the properties we have to use to find ring. So prove that a set Z of all integers, Z is nothing but what? Integers, is a ring with respect to the addition and multiplication of integers as the two ring compositions. So here we have to find addition and multiplication to satisfy the ring. So here the properties under addition. So under addition, how many properties we have? 5 properties. That 5 properties we have to satisfy. So first, closure property, as sum of two integers is also an integer. So if we take two integers, if you add the two integers, that will get integer only. For example, 1 plus 2 is equals to, integers means what now? Integers means what? Okay, the numbers, whenever we add two integers, we get an integer. So by these condition, we are going to satisfy closure property. Next, associative property. As addition of integers is an associative composition, there exists a plus b plus c is equals to a plus b plus c for all a comma b comma c belongs to set. Okay, so whenever we are going to take the integers, three elements will satisfy the associative property with respect to addition. Next, identity, additive identity. So here we are going to use 0 is an element of identity. For 0 belongs to Z, 0 plus A is equals to A plus 0. For all A belongs to Z, there exists 0 is an identity. So next, inverse. We are going to find inverse. So here, A belongs to Z, there exists minus A belongs to Z such that A plus minus A is belongs to A plus minus A is equals to 0 and minus A plus A is equals to 0, where 0 is an identity. Last, in additive, commutative property. Commutative property, A plus B is equals to B plus A for all A comma B belongs to Z. Next, properties under multiplication. We didn't finish till now the problem. We completed only additive properties. 5 properties we finished. Now more 3 properties are left. So properties under multiplication. Under multiplication, first property is closure property. Multiplications. As product of two integers is always an integer. If you multiply two integers, we'll get integer. So multiplication in associate is associate. A into B into C is equals to A into B into C for all A comma B belongs A comma B comma C belongs to Z. So associative property is also satisfied by the integers. Next, distributive law. Distributive law is nothing but A into B plus C is equals to A into B plus A into C, and A plus C into A is equals to A into B into A plus C into A. Hence, Z is adding with respect to addition and multiplication of integers. So all the properties be satisfied by these. Okay, by these 3 properties and the above properties, addition and multiplication, we are going to find the problem. So completed all the properties we used and we satisfied all the properties. Whenever we are going to satisfy all the properties of rings, the problems will be finished. Next, we are going to discuss about division ring. What is the division ring and what is the condition in this? We'll see. A ring R comma plus comma dot is said to be without zero divisor if for all A comma B belongs to Z, A into B is equals to 0, either A is equals to 0 or B is equals to 0. See here, without zero divisor we are taking. Without zero divisor, 2 elements we are taking, that is belongs to R. A into B is equals to 0, that is A is equals to 0 or B is equals to 0. And if the ring R, there exist non-zero elements A and B such that A into B is equals to 0, then R is said to be a ring with zero divisor. So this is the definition of the rings, and we have some examples. First example is set Z comma Q comma R and C are without zero divisors if for all A comma B belongs to Z. And second one is the ring, the set we have 0 comma 1 comma 2 comma 3 comma 4 comma 5 plus 6 comma dot 6 means into 6 is a ring with 0 divisors. The above example is without 0 divisors and the below example is with 0 divisors. Next, we are going to solve cancellation law. In cancellation law, we have 2 properties, left cancellation law and right cancellation. First of all, we are going to discuss about the definition of the cancellation. Let R comma plus comma dot be a ring. See here we are taking 2 binary operators. Then R comma plus is an abelian group. Then cancellation law for addition in R. So first of all we are going to satisfy the cancellation law with addition. So A plus X is equals to A plus Y, that is, so both sides we are going to cancel. A is a common element. A is a common element, so we are cancellation A on both sides. So finally we are finding x is equals to y. That is left cancellation law. Next we are going to find right cancellation. So a plus x plus a is equals to y plus a. That is x plus x is equals to y. So a element is at right side, that is similar. So we are going to cancel that element. So finally we are going to find x is equals to y. That is right cancellation law or satisfied in Next, the cancellation law with respect to multiplication. A into B is equals to A into C. So A is common in right and left. So we are taking A is similar place. So for B we have A is left side. For C we have A is left side. That is we can cancel A on both sides. So finally we are finding B is equals to C. For all A comma B comma C belongs to R. That is left cancellation law. And for right cancellation law, BA is equals to CA, that is B is equals to C. For all A comma B comma C belongs to R, that is right cancellation. So we have similar term at right side of B and C, so that we are going to cancel that. Okay. So here one note we have a ring R is without zero divisors if and only if the cancellation law hold in R. So these are the conditions of cancellation. We have two properties, two conditions, left cancellation law and right cancellation. So we are going to discuss about Boolean ring. Boolean ring. So here the Boolean ring is nothing but two binary operators we are using, and a square is equals to a we have to show in a Boolean ring. So this is the definition. Let r comma plus comma dot be a ring if a square is equals to a. For all a belongs to r, then r is said to be a Boolean ring. So here we have to show that is a square is equals to a. So for example, let S be a non-empty set, then P of S delta comma intersection is a ring where P of S is a power set of S. So P of S comma delta comma intersection is a Boolean ring since A intersection A is equals to A for all A in P of S. This is the example of Boolean ring. Next, we are going to find integer domain. Integer domain. This is the definition of integer domain. Now here we have a commutative ring without zero divisors having at least two elements is called an integer domain. See here, without the zero divisors we have to take at least two elements we have to take. So that is nothing but integer domain. So for example, ring of integers is an integer domain since a b is equals to 0, that is a is equals to 0 or b is equals to 0. For all a comma b belongs to set or. So here we are taking two elements, that is a b equal to 0, non-zero without zero divisors, that all a is equals to 0 or b is equals to 0 we can find. Next, algebraic structure z is equals to 0 comma plus comma dot and q comma plus comma dot and r comma plus comma dot comma and say comma plus comma dot are all integral domains. So this is the condition of integral domains. Next, fields we are going to discuss. Fields. This is also one of the topic of rings, and rings and fields is our topic. So fields is also similar to rings. Okay. A field is a commutative division ring. See here, what is the field? Field is a commutative division ring. Or we have one more definition. Let F be a non-empty set with at least two elements and equipped with the two binary operations defined by plus comma dot respect. Then the algebraic structure F comma plus comma dot is a field if the following properties are satisfied. So we have axioms also, properties also we have, and same properties we have to satisfy. Closure property, a plus b belongs to f for every a comma b belongs to f. And associative property with respect to addition, a plus b plus c is equals to a plus b plus c for all a comma b comma c belongs to set. And identity with respect to addition, here 0 is our identity element. A plus 0 is equals to 0 plus A is equals to A. A is belongs to F and 0 is also belongs to F. Next, inverse with respect to addition. Here B is inverse of A. A plus B is equals to B plus A is equals to 0 and inverse of A is minus A. Next, commutative law. Same with respect to addition. A plus B is equals to B plus A for all A comma B belongs to F. See here, same properties we have to use, but here with respect to multiplication, we have one more property in the multiplication axioms. But in the addition axioms, both are same. Rings and fields are same. Okay. See here, axioms of multiplication means properties of multiplication. We are going to find closure law. A into B belongs to F. A comma B belongs to F. And commutative law, A into B is equals to B into A for all A comma B belongs to F. Next, associative law, A into B is, into C is equals to A into B into C for all A comma B comma C belongs to F. Next, multiplication identity we are using here. Multiplication of identity is nothing but in multiplication we have to take one is an identity element. Okay, 1 into A is equals to A into 1 is equals to A we have to use. Okay, so here 1 is belongs to F and A is also belongs to F. In multiplication, we have to take 1 is an identity element. Next, inverse property. For each non-zero element A belongs to F, there exists an element B belongs to F. A into B is equals to B into A is equals to 1. Here B is inverse of A. We can write B is equals to 1 by A also. So next, distributive law. Multiplication is a distributive law. And with respect to addition, here we are using two binary operators like this. A into B plus C is equals to A into B plus A into C. And B plus C into A is equals to A into B plus C into A. For every A comma B comma C belongs to F. These are all the properties which we are satisfying in fields. See how many properties we have completely. Okay, wait a minute. So how many properties we are going to satisfy in fields? Actually, in rings we are going to satisfy 8 properties. In fields, 3, 5, 4. See here, completely 10 properties we are going to satisfy. 1, 2, 3, 4, 5, 6. 6 plus 5, 11 properties, including distributed. Okay, so we are going to find one problem. It's nothing but one theorem. The theorem is statement is like this. A commutative ring is an integer domain if and only if cancellation law hold in the ring. See here, if a commutative ring is an integral domain if and only if cancellation law hold in the ring. See here, let R be a commutative ring. Suppose R is an integral domain. See here, let R be a commutative ring. R be a commutative ring, and suppose R is an integral domain. We have to prove that cancellation law holding R. So let A comma B comma C belongs to R, that is A is not equal to 0. A we have to cancel, not equal to 0 we are taking, such that AB is equals to AC. See here we have AB is equals to AC. So we are going to transpose AC to left side, that is nothing but AB minus AC is equals to 0. So similar term is A, so we are taking A as common. A into B minus C is equals to C. Since R is an integral domain, so R is without 0 division. There exists either A is equals to 0 or B minus C is equals to 0. Since A is equals to 0, A is not equal to 0, so B minus C is equals to 0. That is, B is equals to 0. See here, we are taking cancellation law. That cancellation law is nothing but AB is equals to AC. By using cancellation law, we are going to find integral domain. Okay. See here, since A is not equal to 0, so that B minus C is equals to 0. That is, B is equals to C we are finding. Hence, cancellation law holding R. Next. So next, converse of this theorem is like this. Suppose that cancellation law holding R. Now we have to prove that R is an integral domain as R is commutative. So we only have to show that R is without zero division. If A is equals to 0, then we have nothing to prove. If you take A is equals to 0, there is nothing to prove. If A is not equal to 0, something we can prove. That is AB is equals to 0. That is A is equals to 0 and B is equals to 0. Or is without 0 divisions. Hence, or is an integral domain. This is the proof and converse of the above theorem. This is the theorem. A cancellation, a commutative ring is an integral domain if and only cancellation lies. So this is my topic. Thank you for giving this opportunity. And first of all, I want to thanks to my principal, ma'am, Dr. Haripriya, ma'am, to give this opportunity. And I want to say thanks to Secretary Sir, S. Praveen Kumar Sir, and DS ma'am, Padmavati ma'am, and Nicola Sir. Such a wonderful chance, such a wonderful platform you are provided to me. Thank you for everyone. Thank you.